How to test the power series for convergence. So we're going to look at these power series where we have the x minus c to the power n, the power series part centered at c, and then we have the an part, which is our infinite series. And together, that series together, we're going to test for convergence. To do this, we're going to use a ratio test. And we're going to find the radius of convergence, which is RR. Okay, so that R represents the radius of convergence. So we know that our interval is going to be from the center plus the radius, and then from the center minus the radius. Okay, so that's going to establish our interval of convergence. So the first thing we're going to do is use the ratio test and find the interval of convergence. And then if the interval is finite, then we're going to test the endpoint for convergence using a comparison test, integral test, alternating series, some other test to test the endpoints separately. So firstly, we're going to use a ratio test to find the radius and the interval of convergence. Once we find that, we're going to test the endpoints to see if we include the endpoints as part of the convergence. And we only do this if the interval is finite. If the interval is infinite, we can just say that the domain of this infinite power series is all real numbers. So taking a look at example 1, we have this alternating series, negative 1 to the power n plus 1, and we have a geometric series part, 3 to the power n, and we have 1 over n as well. And the power series part is x minus 4 to the power n. So we're going to use our ratio test, and this is going to calculate the radius and interval of convergence. So I've set up the ratio here. So I have n plus 1 in the numerator, and I have n in the denominator. So I have all those parts there like that. And I'm going to start grouping these parts to do the limit. So we have the limit as n approaches infinity of the 1 over n part. So I'm going to write this as negative 1 to the n plus 2 over n plus 1. In the denominator, I'm going to have negative 1 to the power n plus 1. And then the n goes in the numerator. Okay, so those parts are going to cancel. We're going to have parts canceling there. We also have the 3 to the n ends up in the numerator. And 3 to the n plus 1 in the denominator. I'm going to group those parts. Okay, and I'm going to simplify those. And then x minus 4 to n plus 1 over x minus 4 to the power n. Well, the n's are going to cancel, and we're just going to be left with x minus 4. That's all going to be less than 1. So canceling out a bunch of parts, I'm going to end up with the limit as n approaches infinity. And for the red portion, we're going to end up with n over n plus 1. And the negative 1, we're just going to end up with times by negative 1. For the exponential part here, we end up with 1 over 3 when the n's cancel out. And then we're left with the x minus 4. And that all needs to be less than 1. Okay, so we can now apply our limit here. The negative 1 really is not relevant, but as we apply the limit to the n over n plus 1, that becomes 1. I'll keep the negative 1 for now with an absolute value. And this becomes x minus 4 over 3. that's all less than 1. And so I can work out the interval for x because when I take away those absolute value brackets, I end up with x minus 4 is less than, I'm going to move the 3 to the other side. And because the absolute value is gone now, we know that it must be bigger than negative 3 or less than 3. So that represents our radius. That 3 actually represents the radius. And then we're just going to convert that into the interval by solving for x. So we have x is less than 7 and x is greater than positive 1. So this represents our interval of convergence. Our radius happens to be, I'm just going to make a note of the radius. The radius is equal to 3. And the interval is going to be so far from negative 1 or from 1 to 7. Okay, at this point we need to test the endpoints. We're going to test these endpoints for convergence. So what we're going to do to test endpoints is we're going to plug the x values. We're going to test x equals 1, and we're going to plug 1 into that expression and then work out our limits here. So we're going to end up with negative 1 n plus 1 over n times 3 to the n. And when we plug 1 in, we're going to end up with negative 3 to the power n. And we want to know if this series is convergent. Okay? So what we can do then is we can do some comparison. I'm going to simplify this into the negatives will cancel out. Okay, so as we include that, we're just going to end up with 3 to the power n. Okay, so when n is even, we're going to have 1 times negative, and so that's always going to end up being negative. And we end up with n and 3 to the power n in the denominator. Those are going to cancel, so we end up with 1 over n. So we have this series is equal to negative 1 over n. Well, this is a diverging series because it is a harmonic series. So we're going to say that this endpoint, when n equals 1, I'm just going to color code this here. So when x equals 1, okay, for all this, this is divergent. Okay. We now have to test the other endpoint, x equals 7. So I'm going to move that down here to give myself some space to work. So if when x equals 7, we're going to test that. So test. So we're going to plug that into our series. Okay, so x equals 7, we end up with 7 minus 4 to the power n. And we have negative 1 to the power n plus 1. We're going to end up with n times 3 to the n. And 7 minus 4 to the power n is going to be 3 to the power n. Again, these are going to cancel out. Now we have an alternating harmonic series. That means this is convergent. Okay, so alternating harmonic means this is convergent. Okay, so therefore we include this endpoint. So we equal 7. Okay, that 7 can be used and it will converge when x is 7, so that endpoint is included in our interval. So our interval is from 1 to 7, or we can write it like this. The interval is 1, not including 1, and 7, including 7. Okay, and just to highlight where this was because it was divergent on this edge and convergent on this edge.